By the night of March 10, 1865, the crew of a massive Confederate ironclad ram made an irreversible calculation. Advancing Union infantry and cavalry forces were rapidly closing the distance to their position on the Neuse River. Surrender meant handing the enemy a heavily armored shallow draft weapon engineered specifically to dominate inland waterways. Escaping was mathematically impossible given the shallow water and the tightening enemy net. The only logical operational decision left was total, calculated destruction. The crew fired briefly at the approaching cavalry, ran powder trails, packed a heavy charge into the bow, set fires astern and amidships, and then abandoned the vessel. The CSS Neuse burned down toward her waterline as the casemate was consumed in the flames. The bow charge detonated, ripping open the port side and dropping the ironclad into the Neuse's shallow mud. A deliberate scuttling after a brief exchange of fire, denying the Union a purpose-built river weapon. The ironclad was a formidable piece of naval architecture. Contemporary descriptions place her at about 158 feet in overall length and about 34 feet in beam. The ship was built largely from local pine, with heavy oak backing behind the armor and dense longitudinal timbers reported as gum. This enormous wooden chassis was designed expressly to support the immense top weight of thick wrought iron armor plating and heavy rifled artillery. As the hull burned through, the surviving mass of timber and iron pressed the wreck down into the channel's soft bottom. But the initial scuttling merely ended her wartime operational career. What followed was a secondary process of systematic dismantling that would permanently dictate the forensic reality of the site for the next 100 years. By the fall of 1865, the war had ended, but the wreck still carried industrial value. In October 1865, the United States Treasury Department auctioned the remains to a New York company, and the following year, commercial crews came to the Kinston Bend to strip out anything that could still be sold: machinery, iron, and guns. Working in the river's murky current, the commercial crews dismantled what remained of the ironclad, pulling the machinery, prying off reachable armor plating, and recovering the guns for the scrap market. When the commercial salvors finally abandoned the site, only what had no immediate scrap value remained: the lower wooden hull, stripped of machinery and armor and buried deep in mud, its casemate gone and its flat bottom left as a hollow, waterlogged tray. Over the following decades, the steady flow of the river current continuously deposited deep layers of heavy sand and fine silt over the remaining woodwork. The thick, anoxic mud completely sealed the yellow pine and oak timbers. This dense layer of sediment starved the immediate environment of oxygen, which effectively halted the biological and chemical decay that would normally consume a submerged wooden shipwreck. The CSS Neuse slipped from the surface world as sand and silt covered most of her footprint. In unusually low water, the stern could still protrude, enough for locals to name the bend Gunboat Bend, before the river covered her again. By 1940, roughly 75 years had passed since the massive ironclad went down in the Neuse River. A private citizen wrote the Army Corps of Engineers to ask whether the wreck could be raised and moved to higher ground. After studying the site, the Corps estimated a recovery cost of about $20,000. But the central problem was not a simple price tag. The report noted the wreck could be visible above ordinary low water. That much of the superstructure and sides had been carried away over time, and it concluded that it was impractical to raise the remains of the hull intact in its present condition. The Corps also stated it did not have authority to remove the vessel. Structural deterioration mattered, but the decisive barrier was the riverbed's mechanical lock. The flat-bottomed hull sat flush on the channel floor, and decades of silt and compacted sand packed tight around the timbers. During breakout, soil adhesion and negative pore water pressures can generate a sticking force far greater than the hull's submerged weight. No airtight vacuum required, just cohesive, compacted sediment that refuses to release. Any lift plan had to beat two numbers: the saturated weight of the bare timber hull, variously estimated at more than 150 tons, and the breakout resistance of compacted sediment across its huge, flat underside. Standard underwater salvage techniques in 1940 relied heavily on lifting barges and surface-mounted marine cranes. Those methods assume divers can rig solid lift points and that the structure can carry concentrated loads without failing. In this case, a straight vertical pull strong enough to break the bottom's grip could have concentrated stress into weakened, waterlogged frames. Instead of lifting a coherent hull, the rigging could have torn through timbers and fragmented the remains while the broad, flat underside stayed locked to the riverbed. That bottom grip kept the wreck down until recovery work began in the fall of 1961. After the Corps' assessment, it was clear that an intact recovery would require changing conditions at the riverbed, not just pulling harder from above. In the fall of 1961, a private team of local citizens tried to invert the usual salvage logic by carving out a controlled work zone around the wreck. From the bank, they swung a massive dragline excavator and peeled away sand and silt, and dumping load after load onto shore until the overburden thinned and the hull's outline began to emerge. To physically reach the lower timber chassis, the salvage team relied on a classic idea, a cofferdam. Instead of working blind in moving water, they boxed the wreck into a temporary perimeter so pumps could lower the water level inside and turn a hostile river problem into a muddy excavation. It was not a perfect seal, cofferdams rarely are, but it offered a fighting chance to work around the hull with some measure of control. The salvage crew built a protective cofferdam around the sunken gunboat to hold back the downstream flow, while heavy equipment cut the adjacent bank into an access ramp. The enclosure leaked, so high-capacity pumps ran continuously against hydrostatic pressure. If they stopped, the river would reclaim the trench. As the level dropped, the vessel's surviving footprint met open air for the first time in generations. Built for inland waters, contemporary accounts describe a shallow draft, often around 7 feet, and in at least one wartime letter closer to 8 feet when complete. And that shallow hull tray was what remained in the muddy pit. At last, crews could reach the timbers at the bottom of the trench. With the current held back, the recovery shifted into a dewatered excavation, and that control carried an immediate structural cost. Pumping the site down removed the continuous buoyant support that had carried the wreck for a century, transferring full gravity loads onto a severely decayed, shallow draft tray with no deep keel to act as a spine. Fully waterlogged, the hull could sag like a long plank and snap if its support concentrated midships while bow and stern hung free. Keeping that bending at bay would dictate every mechanical decision that followed. To extract the deteriorating structure from the bottom of the trench without triggering this structural death sentence, the operation required a completely different set of mechanical leverage. In 1963, a local professional terrestrial house mover named D.C. Murray was contracted to manage the heavy lift. Murray approached the fragile, waterlogged warship exactly as if it were a massive, structurally compromised building resting on a crumbling foundation. Since lifting the structure from above using traditional marine cranes would instantly snap its weak longitudinal axis, the lifting force had to be applied entirely from below, evenly distributed across the entire flat expanse of the underbelly. The house-moving crew systematically deployed a network of heavy mechanical jacks deep into the dirt directly beneath the flat hull. The physical mechanical process was brutal and agonizingly slow. The crew operated the heavy jacks, carefully pushing the massive wooden stern upward just tiny fractions of an inch at a time. The moment the wet timber cleared the earth, the team rapidly shoved heavy wooden cribbing directly into the newly created gap. This immediate backfilling guaranteed that the immense weight was continuously supported across a wide surface area. As the jacking sequence progressed slowly forward along the entire length of the ship, they systematically inserted a series of massive, heavy log rollers directly underneath the lower hull. From these rolling logs were deliberately cut to exactly 45 feet in length. That specific 45-foot dimension was a critical geometric countermeasure. Because the ship possessed a total beam of 34 feet, the 45-foot logs extended completely across the width of the vessel, protruding past the structural edges on both sides. This guaranteed that the rollers provided a continuous, rigid, moving platform directly beneath the flat bottom. The combination of the heavy mechanical jacks, the dense wooden cribbing, and the massive log rollers effectively created an artificial, external spine for the decaying vessel. The precision required during this phase of the operation was absolute. If a single mechanical jack was elevated just an inch higher than the surrounding supports, as the localized upward pressure would immediately punch directly through the softened, heavily waterlogged wood. If the log rollers were misaligned in the mud, the uneven weight distribution would immediately reintroduce the deadly longitudinal bending forces, instantly snapping the frail keel. The terrestrial house-moving crew had to maintain a perfectly level, perfectly synchronized upward push across the entire massive footprint of the historic warship. They repeated the sequence inch by inch, constantly checking level and load distribution. By constantly supporting the entire flat underside simultaneously, the house-moving equipment effectively replaced the missing longitudinal beam strength. The rolling platform temporarily neutralized the severe geometric trap of the shallow draft design, for it physically prevented the massive bow and stern sections from sagging downward, keeping the intense longitudinal stress safely below the breaking point of the aging yellow pine and oak frames. Through extreme mechanical discipline, the team successfully elevated the vessel out of the dirt and onto a stable rolling track. The massive timber structure is raised securely off the riverbed, but moving it overland in one piece guarantees its destruction. In the spring of 1964, transport planning forced the team to choose a controlled kind of damage over an uncontrolled collapse. The massive yellow pine and oak structure had successfully survived its extraction from the muddy riverbed and was now suspended on temporary moving equipment. However, the ultimate objective of the mission was not merely to elevate the wreck. The goal was to transport the entire surviving footprint overland to a permanent dry memorial site several miles away. To achieve this, the massive wooden tray had to be moved out of the river valley, over public roads, and reassembled on stable ground. The immediate logistical boundary was the immense weight and the catastrophic lack of longitudinal beam strength. While the continuous platform of improvised timber supports had temporarily stabilized the flat bottom during the immediate lift, that system was strictly confined to the flat, graded surface of the excavation trench. Transferring the massive, flexible wooden ship from the mud onto standard wheeled transport dollies for a multi-mile highway transit presented an entirely new mechanical crisis. A heavy transport truck relies on a finite number of suspension points. If the flat-bottom vessel were loaded intact onto standard heavy-moving equipment, large sections of the heavy wooden bow and stern would hang unsupported in the open air. The intense gravitational pull would instantly overwhelm the aging timbers. Any attempt to haul the massive structure as a single, continuous unit over uneven road surfaces would guarantee a violent and uncontrolled structural failure. The ship would tear itself apart under its own immense weight long before it reached the destination. The engineering team recognized that saving the historic artifact required a calculated act of deliberate violence. They executed a severe operational methodology known as sacrificial dismemberment. This concept dictates that when the physical scale of an artifact exceeds the carrying capacity of the available transport logistics, and the salvors must intentionally destroy the original structural integrity of the object in order to bypass the logistical boundary. The engineers made the cold, pragmatic decision to systematically sever the historic warship into manageable divisions. They traded the absolute historical integrity of a unified hull for the mathematical certainty of overland survival. The salvage crew deployed heavy saws directly into the massive wooden framework. They meticulously plotted the cutting lines to minimize damage to the primary architectural joints, but the process remained an act of brute force industrial sectioning. They sliced cleanly through the thick yellow pine frames, the dense oak backing, and the solid gum wood keelson. For overland transport to the Governor Richard Caswell Memorial Site, the continuous lower hull was deliberately severed into 3 distinct sections. By dividing the enormous artifact into 3 separate transport divisions, the engineering team instantly neutralized the deadly longitudinal bending forces. Each of the 3 sections now possessed a significantly shorter, more compact structural footprint. This mathematically reduced the overhanging weight and allowed the individual pieces to be safely lifted and loaded onto separate heavy transport dollies. The immense weight of the waterlogged wood was now manageable within the structural limits of the highway moving equipment. Built to be supported by buoyancy, not truck suspension points, the hull had to be cut if it was going to leave the river valley without tearing itself apart. The heavy transport trucks carefully hauled the severed divisions out of the temporary riverbed trench, up the graded embankment, and onto the local paved roads. The temporary cribbing was left behind, replaced by the pneumatic tires and heavy diesel engines of modern highway transport. The convoy slowly navigated the public roads toward the prepared location at the Governor Richard Caswell Memorial Site. The massive sections of the lower hull were successfully relocated, completely bypassing the catastrophic stress limits that would have destroyed the unified vessel. The fractured warship begins its terrestrial transit, forever altered by the conditions of its recovery. The heavy transport operation successfully delivered the 3 severed pieces of the historic ironclad to the designated preservation site. The arrival of the massive wooden sections marked the conclusion of the aggressive terrestrial extraction, transitioning the operation from active structural salvage into a permanent phase of stabilization and forensic reassembly. The heavy cranes positioned at the memorial grounds carefully lowered the distinct segments onto a prepared foundation. The engineering team systematically realigned the heavy yellow pine and oak frames, visually matching the brutal cuts executed during the transport phase. The 3 distinct transport divisions were methodically pushed back together, approximating the original outline of the shallow draft warship. What stood on land was not a pristine, full-length ship, but a remarkable surviving stretch of hull, often described as roughly 140 feet of structure, enough to make the scale of the forensic yield fully apparent. That long-buried lower hull was now available for recovery and study. Stripped of armor and machinery long ago, the flat-bottomed riverine architecture still read clearly in the surviving frames. The heavy timber joints, the specific shallow internal compartments, and the dense gum wood keelson remain physically present for precise architectural study. The raw wooden skeleton stood as a massive, tangible record of extreme wartime engineering, specifically tailored for inland waters. The successful terrestrial extraction of the primary hull also enabled a massive secondary archaeological recovery. During excavation and recovery work in the early 1960s, crews recovered and cataloged nearly 15,000 individual artifacts from the hull's surviving compartments. Trapped low in the structure since the scuttling in 1865, these objects had been shielded by mud and silt from the post-war stripping of machinery and iron. The artifact field delivered the human context the bare wooden chassis alone could never provide. Following the initial outdoor reassembly, the long-term survival of the artifact required another critical transition, exposing the heavily waterlogged yellow pine and oak timbers directly to the open atmosphere introduced a severe new environmental threat. Once exposed to open air, the waterlogged timbers began to dry unevenly. Under sun, wind, and weather, the old wood warped, checked, and split, damage driven not by battle, but by exposure. The structure that had survived fire, stripping, and decades underwater was now deteriorating in plain daylight. To permanently arrest this decay, the reassembled yellow pine and oak lower hull was ultimately moved into a fully enclosed, climate-controlled facility in Kinston. On June 23, 2012, the CSS Neuse was relocated to downtown Kinston, and on July 18, 2013, the Interpretive Center opened to the public. This final transition isolated the historic timber from external weather conditions. The immense physical footprint of the flat-bottomed ship now rests securely indoors, completely stabilized by modern atmospheric controls. Inside controlled air, the surviving hull stands as the physical record of inland naval design and of the hard, practical choices that saved it.